Okay,
All right.
our speaker, Josiah Sugerman. Please.
Hi. I'm going to talk about some interesting tilings, specifically the Quakoversal tiling, which is a very beautiful and complicated looking tiling with the feature that it the orientations of the tiles equidistribute faster than what is possible in two-dimensional space. So what do I mean when I say tiling? So here's a nice tiling. It's called the chair substitution tiling. And what a tiling is you have a shape, maybe like, here we go, here's a square. And a tiling of it is some other tiles. So here are some rectangles whose union is the larger shape, and that intersect only on their boundaries. This is an example of a square which is tiled by two rectangles. And here we have some other tilings. This one is hexagons that tile the plane. They overlap on their boundaries. I'm going to be specifically interested in substitution or hierarchical tilings. So I'll probably primarily call these hierarchical tilings. And what it is you have a tile, and then you tile it by something which is the same shape as the original tile. So smaller copies. So in this case, I have a square, and I tile it with 4 smaller squares. And if you have some sort of tile like this, so if a square can be tiled into 4 smaller squares, you can reverse it and tile a large square with 4 medium-sized squares. So in this case, you have a square, you split it into 4 parts. So here are 4 squares that are half the size. And then instead I could take that square and tile a bigger square with it and carry the 4 daughter squares with it. So in that case, I call this big square, this is the mother square, right? And then this is going to be the daughter square. And then naturally, these are the siblings. So then these guys have the same grandmother. So these are cousins. And you know, the same family lineage that we normally use still works in this case. Like I'll still try to use the same language. So these squares will be these squares will be first cousins, and then siblings, you know, the cousins doesn't really generalize, so I have to call these 0th cousins. And then oddly enough, the square is its own negative first cousin, but that's just how that's unfortunately how our language works, right? Like it doesn't quite generalize perfectly into numbers. So so is my terminology clear? Are there any questions so far? Okay. So that's what a hierarchical tiling is. More explicitly, a hierarchical tiling is you start with some fixed shape, and then you apply affine maps of the form Ci plus lambda I OI, where OI is a rotation and lambda is a rescaling, is your rescaling factor, and then you have a translation. So these are all in this case, the L-shaped tile is rescaled by a factor. So this large L-shaped tile is rescaled by a factor of 2. So you cut it in half, and now you use 4 of the rescaled versions to tile itself. And you have 2 identity rotations and 2 90-degree rotations to the left and the right. So the tile I'm going to be talking about today is the quaquaversal tiling. So in this case, you have a right-angled triangular prism, and this is in 3 dimensions. So you shrink it by a factor of 2, and you tile the right-angled triangular prism with 3 copies of it, with 2 to the 3rd copies of itself, since it's in 3 dimensions. And that means we have 8 tiles. So here we go. So there's 1, 2, 3, 4, 5, 6, 7, 8 tiles. And the rotations are given by, so there are 3 identity rotations. So here's an identity, here's an identity. And here's 1, that's it. And 5 other rotations. And you can check that these are given by whoops. Well, I'll read this one. So you can check that these are given by s squared t cubed, t to the 4th, s squared, s, and st cubed, where s and t are rotations by pi over 2 and pi over 3 about the y and x axis. So let's just look at that for a second. Okay. Sorry about this. Oh, here we go. Okay. So okay, this is sorry about that. Okay, so the tiles are given by a rotation. Okay, well, actually, this isn't that important, so well, not for right now. Okay, so if I had a tile like
just to get it straight, the point is that the these rotations do not generate a finite group.
Yeah, well, yes. In this case, the rotations don't generate a finite group.
And that's sort of the point, right? That is to
Well,
say, we want them
yes.
to generate a dense set of
Yeah.
rotations.
Yeah. So the interesting thing about it is, first of all, it generates a dense set of rotations. Second of all, but there are other tilings in 2 dimensions that generate a dense set of rotations. In 2 dimensions, so there's this pinwheel tiling, which is pretty cool. That generates that generates a dense set of rotations in 2 dimensions. In fact, the rotations of the pinwheel tiling, it's a substitution tile where if you go out, it approaches, it also approaches approximately a uniform, it approaches a uniform distribution of orientations as well, and it's in 2 dimensions. But the rate with which it approaches a uniform distribution is much slower than what's possible in 3 dimensions, because for example, because in that case, it's an abelian group, the rotations in I'm getting ahead of myself a little bit. So so in this case, the orientations of the tiles are given by 1 plus the identity plus the identity plus the identity plus s plus st cubed plus t to the 4th s squared plus t to the 4th plus s squared t squared plus s squared t cubed. Sorry about that. And here S is rotation, is a rotation about the x-axis by pi over 2, and T is a rotation about the y-axis by pi over 3. So you can check that this is true, and it's a little bit hard to keep track of, but it's elementary. It's not that hard to check. And like, for example, I got lost when I was trying to do it just now. So and you'll notice I wrote a bunch of pluses. That's because I want to take a formal sum of these. And the reason I want to take a formal sum of these is when you do a subdivision, you get you're applying these rotations to the original tile. And if I do a subdivision again, so maybe you split up this one, and you split up all of them, then the rotations you get, you would get by squaring it if you applied it twice. In general, the rotations, if you subdivide n times, the rotations you're going to get are this raised to the nth power. And those are going to be the orientations of the cousin tiles in this tiling. And what's going to happen is when I raise it to the nth power, I'm going to get a approximately uniform distribution of tilings, and it's approaching uniformity at quite a rapid rate. In general, so if I had something, if I was in 2 dimensions, then the rotation group is abelian. So what happens is when you raise it to the nth power, you only get words of the form a to the n, b to the n, right? Everything can be put into this form, and things in this shape will grow as a polynomial in n. Whereas things of this, whereas in a non-abelian group, for example, in this group, it will grow in as a it'll grow exponentially in n. So it allows like a much larger possible range of orientations. So it could approach, in principle, it could approach uniformity much faster. And in this case, it does. So. The way you approach uniformity, well, okay. So one measure of one measure that you can take is by one way to measure the rate with which you approach uniformity, or how close you are to uniformity already, is you can take a function. So implicitly, I've been doing this the whole time. I've been associating orientations with elements of SO3. I hope you're fine with that. You just pick a tile. You pick a tile, you call it the identity tile, and then you're like, oh, what rotation did I use to get from the identity to this orientation? And that's just that is going to be the associated element of SO3 with the orientation of the tile, right? So however I had to rotate this to get this, in this case, it is I guess that is the one I called. This one is the one where you rotate it by S first. So I guess this one is ST cubed, the way that I wrote it. So in this case, it's ST cubed, I think. And so you in order to get that one, you rotate by pi over 2 about the y-axis, and then you rotate by pi around about the x-axis. So hopefully I didn't mess that one up. Okay. So anyway, you have this formal linear combination of elements of SO2, and that corresponds to a probability distribution. So if you were to on orientation, so if I picked one of these orientations at random, and I had a function on orientations, so this is going from SO3 to the reals, let's say, then I can measure how close this is to a uniform. I can measure how close this distribution on orientations is to a uniform distribution by just integrating the function with respect to this distribution. So you just average it over that distribution. So in this case, if I had the nth subdivision for the tiles, I would sum over everything, over all of the tiles in the nth subdivision, over all their orientations, and then I would average. So I guess I would have to divide. There we go. And then I would average. The function. And then I would compare that to integrating with respect to the uniform distribution. So if I can show that this is small, so then it shows that it converges the uniform distribution very rapidly. I guess I did lowercase n over there, so it should be a lowercase over here. Okay, so this is the sense in which the in which this will approach uniformity very rapidly. So here the WN are words of length n in the orientation of these tiles, right? So in 1 + 1 + 1 + s squared t cubed plus t to the fourth plus t to the fourth s squared plus s plus blah, blah, blah. Okay. So this, so averaging operators of that form yeah, averaging operators of that form can be broken down into can be, so if I have an averaging operator of that form, it can now I'll average any element of L2. So L2 SO3, why not? And in this case, you can always decompose. So it turns out that you can write L2SO3 as a direct sum of irreducible representations. Oh, I'll call it H, why not? Sure. H, 2K plus 1. And think it has multiplicity 2K plus 1. And these operators fix all of the irreducible representations. So wait, so let me point out what the representation on this is. So what's the intuition here? So you notice I had an operator that looked like this. Yeah, and an operator that looked like this. So GI is in some generating set. Yes, let's see. This is actually a representation of so the GIs are acting on some function. F is going to F of GI. So what is the action on F? GI dot F equals, let's see, equals of Z, I guess, equals F of GI Z. So here Z is an element of SO3. F lives here, so it's an integrable function. Well, I guess square integral. Well, it's an integrable function. It's because SO3 is compact. So G dot F. So the action is given by actually this technically, but is given is given by this. So this is just a linear combination of elements of the group acting on a function. And the Peter-Weil theorem tells you that you can break down this, that tells you what the irreducible components of this representation is. And in this case, it just acts on homogeneous polynomials of degree homogeneous polynomials in two variables of even degree. So, you know, those are what the irreducible representations are. So by the end of this discussion, you now know this. So we started with this operator, F goes to 1 over, I guess, the generating set S. So GI in that generating set. And then you ended up with this F GI inverse. Oh, forget about the inverse. It doesn't matter. See. This is spinner. So you start with an operator that looks like this, some sort of averaging operator. And then studying this operator is the same as studying this infinite family of finite dimensional matrices. And now, so P, this is just a certain homogeneous polynomial. Oh, okay. And then it maps to, and then you just take so I hope this is clear. Okay, but now this is an action on finite dimensional spaces. So equivalently, so these are all of the irreducible representations. Okay. So now instead of you needing to study this, you can instead study, just look at polynomials, just see what this does to homogeneous polynomials in two variables with even degree. So in the case of, in our situation, we're looking at this operator. So here I'm again, I'll remind you, I'm rotating about pi over 2, and I'm rotating about pi over 3 with orthogonal axes, and then I have an element that looks like this. You just so Conway and Radin were able to show that we're able to describe like the relations in this group. So we've boiled everything down to studying finite dimensional representations where it's a formal linear combination of this form, and you have S and T, and S, and they satisfy these relations. S squared T equals T inverse S squared, and ST cubed equals T cubed S inverse. So so the primary questions of interest are to, first of all, show that to show that if you have this operator, it's to show that like if you wanted to show rapid equidistribution, the way to show that is you compute the eigenvalues of this operator, and if it approaches uniform distribution, if it's close to the uniform distribution, what does that mean? That means if I average, what is a uniform distribution? That means when I average things, I get the same thing. So in other words, if it's close to the uniform distribution, it means if I average things, I need to well, so well, that's not true. If it's close to the uniform distribution, that means that well, being close to the uniform distribution means that actually it means the like almost the opposite of what I said. It means if you're on the if you are if you average if you apply the averaging operator at well, anyway, rapidly approaching the well, okay. So the two primary things of interest are to show that the eigenvalue, to show that there are no eigenvectors near one. Well, to show that there's a spectral gap between the largest and second largest eigenvalue. This means that, like, if I okay, so I think what the way that you show rapid equidistribution is by showing that there are no eigenvalues near one besides the trivial eigenvalues. So the only functions that are close to themselves when averaged are the constant functions. So you have to have a large constant component. So the two primary things, primary questions of interest are to show that this does not have eigenvalues near one, So here are the two things of interest. This does not have eigenvalues near 1. And then another thing, which is more of sort of an observation. I'm actually not sure why this is important. I'm sure why something does not have not having an eigenvalue near 1 is important, but I'm not totally sure why having a real spectrum is important in this case. Like it seems more like an observation. But anyway, so there's a question like it was observed numerically that this has a real spectrum. So that's what I'm going to try to show right now. Okay, so let me restate the I can now restate the conjecture, and if you were confused about anything, that is fine. There will no longer be, if you can just pay attention from this point on, there will no longer be any confusion. So here's the new question. S, show that S 1 plus 1 plus 1 plus S t cubed has a real spectrum. When so S and T are just free except for these relations. S t cubed equals t cubed S inverse. T to the 4th. Well, T S squared equals S squared T inverse. And then S to the 4th is 1. So this is a rotation by pi over 2. So this equals 1 and T cubed, T to the 6th equals the 1, okay? And so for a unitary, so what does that mean? S inverse is the complex conjugate for finite dimensional unitary representations. So this is the conjecture, or this is equivalent to the conjecture. The conjecture that it has a real spectrum, which was observed numerically by Sadun, Weirin, and that little dragon. Okay. So this is the question. Are there any questions about this? About this, or even anything that was said earlier? Okay. So okay, let's try. So now let's try to show that this operator has a real spectrum. The way that we're going to do it is as follows. So first of all, we can just ignore a bunch of this stuff right off the bat. So you see there's this one a bunch of times. So to be totally honest, there should be this 1/8, right? This is the conjecture. This has a real spectrum. So you see there's 3 copies of the identity matrix. So in other words, so right now S and T are just matrices, and they are I guess like they are odd dimensional matrices, but maybe that doesn't even matter. Yeah, I mean, it's going to turn out that they have to be odd. So they're matrices, they're odd dimensional, they're unitary, meaning S inverse is S star. And that's what we know about them. And let's just mess around with these matrices until it becomes clear that this is a real spectrum. And then the numerical observation will make sense. Oh, I see two chats. What is the spectrum of a formal sum of rotations? Oh, that's a great question. So the spectrum of a formal, so if you take a formal sum of rotations, you can get a, oh yeah, that's a good point. If you think of each rotation as an operator on that, then yeah, obviously, yeah, that's a really good point. It's just the regular sum, it's not the formal sum. And the spectrum of a formal sum of rotations is the way that I was stating it is you take the formal sum and then you see what it does to all of the irreducible representations. But actually, I'm not even sure which one I picked. They're the same. Yeah, but yeah, that's a good question. Okay, so okay, so now we're going to show that this is a real spectrum. We just so now okay, so let's clean this up a little bit. We don't need these ones. They are garbage. They don't do anything. Okay. Fine. The ones don't do anything. And the 8 doesn't do anything. So now we just need to look at these elements. It's still going to be real even with that. Okay, so now what I'm going to do is I'm going to find a really good partition of and to do that I'm going to decompose so I'm going to find a really good partition of the irreducible representations, and to do that I'm going to decompose the irreducible representations into vector spaces like this. Into the simultaneous eigenspaces of t cubed and s squared. What's t cubed? T cubed is just the rotation by pi. Is just, yeah, and s squared is the rotation by pi in the perpendicular direction. Okay, so now you have these subspaces of the representation, the simultaneous eigenspaces. So t cubed, so remember, this is t cubed is a rotation by pi, so t to the 6 is a rotation by pi over 2. So that means t cubed squared is equal to 1. So that means alpha is either 1 or -1, and beta is also 1 or -1. So therefore, I have a partition using the simultaneous eigenspaces of t cubed and s squared. You get a partition of the representations into 4 orthogonal vector spaces. So, and I will, and they're called lambda 1 1, lambda 1 -1, lambda -1 1, lambda -1 -1. So depending on the eigenspace of s squared and of t cubed. So so here, for example, for all the vectors on this space, for example, s squared is equal to s squared. If you apply s squared to the vector, you get negative the vector, and if you apply t cubed to the vector, you get 1 times the vector. So you split it up into those eigenspaces, and it will turn out that that things are this form. So that's something of the form s plus st cubed, but also something of the form t to the 4th plus t to the 4th s squared. So in other words, you take a vector, you take a rotation, and then you rotate it by, so here u and v are assumed to be orthogonal. So if u and w are orthogonal, oh, I guess I use v and w, whatever. Okay. So here v and w are orthogonal. So that includes this case and this case. It will be, first of all, lower block triangular with respect to this partition. So here's a matrix, and I've partitioned the vector space, the representation into these 4 subspaces. It's lower block triangular with respect to this, and it's Hermitian on the blocks along the main diagonal. So that this is sort of the main theorem. And then when that happens, then this sum is still going to be lower block triangular and Hermitian on blocks along the main diagonal. And then finally we have to deal with s squared t cubed, the last term. And this one behaves even better, right? This is equal to, on lambda alpha beta, this is equal to what's happening here. So one of these is going to be just, so if I live here, then one of these multiplies it by alpha, and the other one of these multiplies it by beta. So this is just alpha times beta on here. It's just a multiple of the identity. So that's even better than these guys. You know, these guys are Hermitian on the blocks along the main diagonal, and this one is actually diagonal. And when I add all of these together, I'm going to get a matrix which is lower block triangular and it's Hermitian on the blocks along the main diagonal. So that means, so if you're lower block triangular and the only entries are over here, that means that all your eigenvalues come from these blocks. And that means that since these blocks are Hermitian, all the eigenvalues of this matrix has to be real. Okay. So once you prove this theorem, we have a proof that this operator has a real spectrum.
Sorry, I'm a little bit confused that you have that theorem. And
Well, I didn't prove it yet. Well, yeah.
I know, but you've got it for particular vectors v and w, and both s plus st cubed and t to the fourth plus t to the fourth s squared are of that form for appropriate v's and w's, but aren't they different v's and different
Yes.
v's?
Yeah, that's a good point. So the different v's, one of the v's and w's is x and the other one's y. So one's x and then y and the other's y and then x. So it turns out that it's low. It turns out to be lower block triangular in both cases.
Okay, cool.
Yeah, that was a really good point. Okay, so yeah. So so yeah, now let's prove that the let's prove the main theory, this theorem 1 right now. Okay, so there are a couple of little miracles that happen. So first of all, let's break it, and let's break the representation of this rotation into a Hermitian and skew Hermitian part. So the Hermitian part of this representation commutes with both with both of these rotations. So in and the so it's not hard to see this. So here's one example. So I have S plus S inverse, and so the same thing works for T, of course. And then I apply, and then I move this to the other side, and then the S becomes an S inverse. The S inverse becomes an S. Okay, so so the Hermitian part commutes, and it's even better for S squared. It's even better if it's about the same axes, because you don't even switch these guys. Okay. And the skew Hermitian parts anti-commutes. So here it switches, but now it does make a difference. This is negative that. So, but on the other hand, the skew Hermitian part commutes when it's about the same axis, when it's a rotation about the same axis by pi. Okay, so when it's a rotation about the same axis, these don't move, and it just commutes normally. So when we combine those two facts, what happens is the Hermitian part leaves lambda alpha beta invariant, and the skew Hermitian part leaves one of the axes, one of the leaves one of the components invariant and negates the other one. So what ends up happening is you start out with a situation like this, where it's, so what ends up happening is, you start out with a situation like this. So this guy's going between here and here, and this guy's going between here and here. And then, so what is this? This is what our, what RV theta is doing. So RV theta is, it has a component, its Hermitian part is fixing this, and its anti-Hermitian part is swapping these guys. And so its Hermitian part is fixing this, its anti-Hermitian part is swapping these guys. And then when you apply RW pi to this, well, what is that going to do? On one of these guys, it's going to negate it, and on the other guy, it's going to leave it the same, right? Because this just multiplies it by plus or minus 1, depending on if you're in alpha or beta. So it's going to negate it when it's coming from here. It gets negated. So the arrow going up is deleted. The one going down is doubled. So it ends up being like this. So this arrow going up is cancels, and the arrow going down gets doubled, right? So that's what happens when you add RV theta to that. Okay. So, okay, and that actually does it, because how do you arrange it so it's going to be lower triangular except for on the diagonals? Well, you have this one. For example, you first go here and then you go here, and then actually it goes to 0, oddly enough. And for this one, you go here and then go here. So for example, this order will make it lower triangular. Well, yeah, this one first, then this one, and then this one, for example, makes it lower triangular. And then in the case of the operator that we're concerned with, the red arrow, so actually this is, to be more precise, this is what happens. So maybe I should, in one case, you have these blue arrows that, so this is how this is what happens with the S's. The S's treat the subspaces like this. First you start here, and then you head down, and then you start here, and then you head down. And then, so that's what happens when you're, for the rotation about the x-axis, well, I might be mixing them up. This might be actually y. Well, whatever, it doesn't matter. Okay. So the rotation about the x-axis. And it actually rotates it if you are starting with y and then doing x. So this is a more precise description of what's going on. let me make this red. So the red ones are the T's and the blue ones are the S's in this case. Okay, are there any questions? All right. So I should probably end now, unless yeah, I'm already a minute over. I guess it's a good time to end.
There's plenty of time in the universe, so oops. Yes, let's thank our speaker. Let me see if I can.
Thank you.
There we go. Okay. Josiah, any questions for Josiah?
A couple of comments, basically what we were thinking way back when. And you know, and again, Draco gets most of the credit. Is that you know, I was really surprised that the spectrum wound up coming out all real, and it just was a mystery to me. And in fact, I remember meeting Sarnak at a conference and pointing this out to him and said it's real. And he said, well, real things aren't so strange. If it's not Hermitian, you get, if you have, say, some a weighted L2 space instead of regular L2 space, you get Hermitian. And it's like, but this is not anything like.
In fact, I can prove that it's not. Like, so one of the interesting things is like, you're like, well, maybe it's like, maybe we had the wrong. Okay, so I was working on this for a really long time, and I was trying all sorts of stuff. And one of the things I did was I was like, okay, maybe there's a way to transform it so that it's not like it's not the standard unitary inner product. Maybe I can just do some sort of transformation and show that it's unitary with respect to a different inner product. I can prove that it's not even it's not unitary with respect to any inner product. I really think that this is the only way to do it.
Right.
Like,
and then of course, once you've got that it's real, that makes the questions of how quickly do you converge the ergodic average cleaner, because you're not saying let's keep eigenvalues away from the unit circle. You're just saying let's keep eigenvalues away from 1.
Oh yeah, that's a really good point. Yeah, that's so true.
And actually, once you have the 3 plus other stuff, I mean, the only eigenvalues of 3 are 3.
Right.
So that means that the only place on the unit circle that an eigenvalue could be accumulating is at 1. And I was just shocked when I threw this thing at MATLAB, and it's just, it's like a 10-line MATLAB program. It's really simple. And real eigenvalues, real eigenvalues, real eigenvalues, real eigenvalues, and they seem to creep up towards this. I mean, they certainly looked like there was a spectral gap, but it was a really small spectrum.
Yeah, no, I'm very surprised that you were able to tell that that you looked at it and were convinced that there was a spectral gap. How were you able to have some idea that it was a very small spectral gap?
Well, I mean, if you look at what is the biggest eigenvalue up to a particular representation, then let's see. Then like the record eigenvalues, you get above 0.9 by the time you get to the L equals 18 representation.
Right.
And by the time you get to the 45th representation, you're at 993.
Right.
And we took it up to the 300th representation, and we never got above 994.
Oh, I see. So you're like, it seemed to be stuck there.
It gets to 993 reasonably fast, and then it's never gets above 99381, and well, maybe that's the ceiling.
So
and we don't have any proof of that. I mean, these days computers are a whole lot better than they were 25 years ago. So I'm tempted to just rerun the exact same MATLAB program, only push it out to 1,000 instead of 300.
So
worry about
I don't
how
know
long it
why I
takes.
skipped this. Oh, I guess I do know why. I got caught up on some stuff. But so Bourgain and Gambourg showed that there is a non-zero spectral gap by showing that every if it just anything with algebraic entries is going to have a will end up having a non-zero spectral gap. So so it's non-zero, but I don't know how to extract lower bound from their method. Maybe it's just like a lot of work, but I think I have a feeling that I feel like, okay, so one of the things I did not get to, maybe I'll share my screen right now. Why not? One of the things I did not get to is, so you get a lot out of this. So it turns out that that you can write down what the blocks actually look like. One of them looks like 2. The other one, the other one looks like 4. One of them looks like negative t plus t inverse plus 2. So you have these really trivial eigenvalues. Like, so I can say exactly what 3/4 of the eigenvalues are, and one of them looks like this. So all the eigenvalues come from s plus s inverse plus t inverse, and then translated and divided by 8. So and this is a nice simple Hermitian group element with that I feel like you should be able to use Peter Sarnak's method to show that it has a spectral gap. And I like you have a lot of the ingredients. So like from your paper and so Sarah was able to show that there was that the group is that it's an S arithmetic group. And in your paper there is this, you have this explicit way of writing down what all the elements are, and it looks like you can carry out most of Peter Sarnak, what's in Peter Sarnak's paper, but but I know that I don't quite understand some aspects, because when I just, so if Peter Sarnak's paper worked the way it did literally, right? So Peter Sarnak's paper only gives you the best bound, that Ramanujan graphs paper. So you would have this insanely good bound, and then I had some argument where actually it was going to be smaller, but it's like it should be a transformation of this perfect bound, but it's still like a factor of 10 too big or more. So yeah, it's about a factor of 10 too big. So I know that I don't quite know what to do, but I feel like most of the methods should transfer over.
Yeah, and the other thing I wanted to point out was sort of the motivation for all of this.
Oh yeah, why?
After they studied the pinwheel tiling, that Charles was really into the question of, could this actually model physical materials? That this would be a material that you have a theorem, in the limit it's round. And I pointed out that, well, it's round, but not very round, because the total number of orientations after you do n generations is only 8n. And the volume is growing like 5 to the n. So you're approaching roundness logarithmically, and that's useless.
Yeah.
The log of the size of the universe is a reasonably small number, and so that doesn't do any good.
Mm-hmm.
So back to the drawing board, and John and Charles wrote down this Quakoversal tiling, and they said, aha, now we're in 3 dimensions. 3 dimensions is non-abelian. The number of words in the generators grows exponentially in the word length. And so that means that the number of different orientations that you get is going to grow as a power of the volume instead of as a log of the volume. And the point of this paper with Draco and Van Veeren, and by the way, it's not Weeren, it's Van Veeren. I mean, Van is part of the last name.
Oh, I see. Sorry.
So it's Van Veeren, Doug Van Veeren. He's a real person, and Draco is not a real person. Sorry, Draco. You're special, but in a different way. And the point of that paper was to say, well, yeah, it's polynomial, but if you're going as the 300th something root of the volume, technically it's polynomial. To a mathematician, that's polynomial. To a physicist, that's log.
Right.
Right. That you take something, you take something the size of the universe, and it is never going to be anything remotely round.
Well, yeah, the improvement was it went from universal scale to galactic scale, right?
Yeah, yeah. Right. So you go from the log to the 300th power, and that's the point, that you have a spectral gap. And I mean, we guessed that we had a spectral gap. We had no way of proving that there was a spectral gap. We just said, hey, look, the computer seems to be topping out. We think it looks like there's a gap there.
Right.
But when you have a gap at 0.94, but 0.994,
right.
That means that it takes the 250th power to get to 1 over e.
Right.
Okay, 250th power, you subdivide 250 times, you've got 8 to the 250th particles there. This is kind of big. It is the galactic scale. Maybe it's the universe. And before that you could never imagine a chunk of material that you can hold in your hand. That's only 10 to the 23rd particles in a mole. So okay, maybe 10 to the 30th if you got a big chunk, but it's nowhere near 8 to the 250th. So you're just not going to damp out all of those eigenvalues near the top of the spectrum.
Yeah, I was thinking about there's
it just doesn't look round.
Yeah,
even though the mathematician.
Oh, do you have any so you probably looked for tiling with a 3-dimensional tiling with like a gap that is actually good. Were you guys able to find
No, it didn't play. I mean, the point is that the Quakoversal was the proof of concept. It's that hey, you can do this in 3 dimensions. You can make everything polynomial. And I think that I'm the troublemaker, the one who says, nah, it's not going to work. I don't appear on ads for crypto, but
yeah, but I mean, it would be very
it's never going to work, and saying, look, these numbers are just too big. And I think that by then Charles and John were just interested in other things, and it's like, fine.
I mean, it would be very, very extremely satisfying and cool to have a material on your desk, which was
it would be. It really would.
Yeah, or even to have a tiling on a computer would be nice. And I see no reason, which is I see some intuition why a tiling like theirs would be so these simple tilings where things are like almost planar, you have 2 planes, there's this little rotation, you needed so it's very, very close to if you remove maybe 2 of the tiles, then you have a planar tile. Then all these tiles are like SO2 plus a reflection, right? Like you get rid of maybe one of these tiles. So it's in a way it's very, very close to this 2-dimensional tiling. So from an intuitive point of view, you could see that it seems like, yeah, it should probably have a really small gap. But I see no reason why maybe even a generic three-dimensional hierarchical tiling would not have a fairly large gap. You know, like if you take three random rotations, it's
Well, I think the way
there's a
that
huge gap.
the way to get something with a bigger gap
Mhm.
would be to add some randomness to it. And that's things like, if you think about the way the quaquaversal is made, it's made from this deterministic tiling with only a few rotations, then says, over here, let's twist it by 90
Right.
degrees.
Yeah,
Let's twist
exactly.
this bit by 120 degrees.
Mhm.
Well, what if you twist it sometimes by 90 degrees and sometimes by negative 90 degrees?
Mhm.
Just flip a coin. And if you just flip a coin as to whether to rotate this by 120 or by negative 120. And that might get you, that might be something that would give you faster convergence.
Right. Yeah. You just choose between. Yeah, you can have these very similar. It's very easy to even accidentally do the wrong tiling. There are these very similar tilings that fit in that shape, and you just like swap out which one that you want to use at any given step.
And there have been some guys, there's some guys in Europe that have been doing some nice work in the last few years on random tilings, random substitutions.
Mhm.
And most of their work is one-dimensional. Because already things get, I mean, they're not talking about the geometry of the tilings, they're just talking about ergodic measures and the combinatorics and stuff like that. But Dan Rustin and his collaborators. But I think that if you wanted to get something that really approached roundness nicely in 3 dimensions, that you'd want to bring in their toolbox.
Oh, I see. So, yeah. So, right. Yeah, I think it would. I sort of have a feeling that, well, it's hard to make 3-dimensional tilings by hand. Like even just trying to make one that you don't even already know, just making a tile. So
It's nice to piggyback off of John Conway.
yeah, exactly. so I feel like the randomness, inserting the randomness is a good hack when you want to. Though I do believe that. Why do I believe? I believe that I know it is conjectured that that with high probability random elements of SU2 have asymptotically optimal spectral gaps, and I see no reason why a typical there's this constraint, but I don't see why it would stop you, the constraint that it has to be a tiling, but like I see no reason why a typical tiling shouldn't have a large spectral gap. And but I don't know how to maybe there's a way to search for it on a computer, but I don't know how to just draw a typical tiling, right? So yeah.
You need somebody clever, and
Right. Yeah.
I think we can all agree that John Conway was clever.
Yeah. So yeah, that's how it is.
Any other questions, comments for Josiah? If not, thank you again for lovely talk.